It's an honor to be here and give the energy seminar here at Stanford, which is one of the best attended seminars I think that there is. But I've taken the opportunity today to kind of compile a little bit of greatest hits, but also some of the latest stuff that I've been doing with the group into a package that you see I call the tough stuff in a colloquial way, really thinking about the most difficult to abate greenhouse gas emissions. But I kind of want to kick off with just a little bit of history for those of you who haven't been at this quite as long as Adam and John and I, what the history of quote unquote solving climate change has looked like over the past 10 or 15 years. And I'll date myself a little bit and say, when I was a graduate student, a very important paper came out in 2004 led by Steve Pacala and Rob Socolow at Princeton University. And this was the title. You can see that they have solving the climate problem in there. And really what they said in this paper was that we might implement what they called wedges in order to head off the upward trajectory of greenhouse gas emissions and flatten those emissions for a 50-year period. The reason I'm calling this up and starting to talk with it is just to really make the point that in 2004, 20 years ago, we thought solving the climate problem meant stabilizing emissions for a 50-year period. That's a pretty different cry than what we're thinking about later. Around the same time, folks really for the first time, and this is more from Professor Wyant's world of integrated assessment modeling, started thinking about, hey, maybe we should run these scenarios not just looking at population growth and economic growth that we think is plausible, but actually impose some climate policies in the scenarios to see what might happen. Could we actually get emissions to come down? That was actually pretty rare at this point in history. Most times we were just projecting plausible futures without actually saying that we might intentionally try to reduce greenhouse gas emissions. Just for context, I've added these red circles to all these plots to show where we are today. And you can see that we apparently failed with our stabilization triangle, but we're pretty squarely in the middle of a lot of those integrated assessment model scenarios. So something else that happened just a few years later, which took us from the world of maybe just stabilizing emissions and moved us toward where we are today, and that is a lot of geophysical research started coming out and showing that greenhouse gas emissions cumulatively are proportional to the amount of mean temperature increase globally. And so we get plots like this from the most recent IPCC. What you see here on the x-axis is cumulative CO2 emissions since the industrial era, and the vertical is the warming since the same time period. And you can kind of see the historical is mostly a line there. And then in the future, you get different colors depending on what trajectory we may be on. But the point here is that these are essentially lines. So that means for every increment of CO2, or rather every molecule of CO2 we add to the atmosphere, we get another increment on the global thermostat. And that's really the case on human timescales. The upshot of this is that we have what amounts to a finite carbon budget in order to stabilize the Earth's climate really at any level. And that could be a level that we want to avoid maybe under, say, the Paris Treaty or some higher amount. But this also then has this corollary that solving climate change means that we need net zero greenhouse gas emissions of long-lived greenhouse gases. So essentially, if we add CO2 to the atmosphere, we need to have that amount of CO2 coming out of the atmosphere in order to not increase the concentrations. This is actually, as you see, relatively recent that we really started thinking about it this way. A few years after some of those papers about the cumulative relationship, we got towards what we call deep decarbonization. So these are just a selection of papers. A lot of you may remember this era when people were talking about how could we actually get emissions 80%, 90% down from where they are today. But it was kind of with this backdrop that a group of about 30 of us, including a bunch of folks from Stanford, including Sally Benson, Inej Azevedo, Chris Field, Ken Caldera, all got together and we decided to have a meeting where we would actually think not just about this deep decarbonization, but try to understand what would be entailed in actually reaching net zero. So to get to the finish line of getting to the point where we're not increasing the concentrations of CO2 in the atmosphere. And the important reason, besides all of that science that I just showed you, is that we were recognizing something else very important that now I think all of you understand, and that is that solar and wind and batteries were all coming down in cost, really remarkably. And so you can sort of see on this timeline of solar costs when that stabilization wedges paper came out, when the deep decarbonization era was going on, and just how much those prices were falling. So this was the sort of subtext that led us to have this meeting, because we recognized that this stuff was going to beat fossil fuels on cost, at least for a lot of the day. And I think it's not really possible to argue that solar is going to be nearly free in the middle of the day, if it's not already in the next year or two. So what did we do? We got together, about 30 of us, in an Aspen ski resort, and we met for a week, and we brought folks who knew a lot about a lot of the really difficult parts of the energy system. But I want to talk through that. So this is a pie chart of global fossil fuel and industry emissions. It's a little dated now, 2014, but it's actually not so different than what we have today. And you see those parts of the pie chart labeled electricity and the shorter distance road transportation and residential. These were the parts of the pie that we thought, if there was really cheap renewable electricity and affordable lithium-ion batteries, that we were actually going to be able to solve. So the easy parts, if you will. Of course, nothing is easy, right? We have a lot of work to do. We know just getting a lot of solar and wind built is a challenge. Getting more vehicles that are electric on the road, getting folks to buy heat pumps and use those. So it's not easy, but it's relatively a clear-cut path. If we have that cheap renewable energy, a lot of this stuff becomes affordable. The pieces of the pie that are sticking out are the ones that we thought were harder. And I'm going to say more about what I mean by load following electricity, but the idea here is, of course, we don't always have the sun and the wind, and we may have demands when we don't have those resources available. So how to close those gaps. This iron and steel and cement, I think probably a lot of you are familiar. These structural materials come with a big emissions footprint, and as I'll explain more in a minute, they're just difficult to decarbonize for a lot of reasons. And then there's this sort of transportation piece, not the light-duty vehicles, but long-distance transportation, aviation, shipping, things like that. These are the three buckets of tough stuff that we identified in that meeting. And the important point that came out of it was, even if you just looked at these tough things, it's about a quarter of the total. So it's not a small share of the total pie. And really, these are going to be the things that define how quickly we can reach net zero. The cheap stuff, the easy stuff, is probably clear-cut. So let's talk through each of these and some research that we've done over the years, starting with electricity. So just to say, the way that we tackled this problem was, I think, in an effort to be really simple and reduce it to its core fundamental principles. So a lot of people run energy system models, and they give their models different technologies, and they hypothesize different costs for these technologies in the future, and they look to see how the system reaches low emissions at least cost. That's a very fruitful line of research. What we wanted to do was actually say, let's pretend that we're just going to try to get electricity from solar and wind. How much can we do with just those technologies, and how much does just the geophysical variability about night, days when the wind is not blowing, how much do those constrain us? So what you're looking at here is about 36 years of weather data from the continental United States, and it's showing the variability of these different resources. So the purple, for example, is wind variability. You can see it's all over the place. There's a lot of variability in that. It tends to be highest in the wintertime, so on the either end of this plot, and it dips in the summer. And it's pretty well complemented by the solar resource, which is that yellow curve. You can see there's a lot less jagged peaks around the solar. It's a more reliable resource. We know when the sun's going to come up. And that it's usually up. Even if it's a cloudy day, it doesn't completely get dark. And so that solar is the opposite. It tends to be best in the summer and worst in the winter. And just for comparison, you see what the demand has been in recent years on the orange curve. And that's showing that at least at this point, we still tend to have peak electricity during the summer when we're using a lot of electricity. I say at this point because when we get a lot of vehicles or we start electrifying our heating, that profile could change, but that's kind of what it looks like. So what we did is to think about if we wanted to supply the U.S. electricity demand in every hour, but we only wanted to use solar and wind to do that, how many of those hours could we actually meet demand? So we hypothesized systems that had either all solar, which is at the top of this plot, or all wind, which is at the bottom of this plot, or some mix of the two, and that over the course of the year, this mix of solar and wind generated exactly the number of megawatt hours of electricity that is demanded within the year, but of course not necessarily in the same hours as the demand. And then this plot also shows that we looked at whether you concentrate all of that generating resource in a small area, or if you want to try to accommodate some of the variability in wind, for example, you like to spread things out because it might not be windy here today, but it might be windy somewhere else that's a little further away. So spreading out your resources helps. So what you see in the contours is the fraction of hours that we thought you might actually be able to meet demand given those constraints that I just mentioned. And really, I think the thing to say is you see that a system that's wind heavy tends to be the most reliable. I should have said this is also hypothesizing no energy storage. So we're not able to generate and carry any of that electricity over. So wind is always going to be better in that case because if you have no storage, having a solar system is never going to get you more than about 50% because of night, right? So that's a wind-heavy mix, but if we add 12 hours of storage to overcome the diurnal solar variability, you see we shift towards a more solar-heavy system, and maybe we get to the point of meeting demand in, say, 80-85% of the time. Something to note here is that as we go from left to right, and remember this is saying we're spreading out those generating resources more, in a system with no storage, it seems like that actually helps us a lot. Here's a wind-heavy system, spreading it out. Actually, we cross a lot of contours as you go from left to right, versus a system when we have storage, doesn't look like it's as helpful. So we're using solar. We actually want to put that in a relatively small area where there's really great solar resources. There's an important finding here because it sort of suggests that we might want to bet on either a transmission grid that's very robust and a wind-heavy system, or a solar-heavy system with a lot of storage, but maybe it won't make sense to do both of those things. We also then ran simulations where we, what you might call, overbuilt the system. So these are systems now that instead of generating exactly the amount of electricity within a year that we demand, they actually generate 150% of the electricity that we might demand. It's kind of a theory like if you had a car that wouldn't start every day, you might buy two cars and maybe one of them would start, right? That's kind of the fix here. And you can see it does better, right? You get brighter colors, you meet more percent of the hours. And maybe by the end, in that bottom right where we have 12 hours of storage and we've overbuilt the system, we might get up to sort of 99% of the time. So within each panel, we're looking at the benefits of transmission. From top to bottom, we're looking at the benefits of overbuilding. Left to right is the benefits of having storage 12 hours. And again, if we really do all of these things, it looks pretty good, right? We're getting to 99%. We maybe think, okay, we can do this just with solar and wind. Who thinks we can do it all with just solar and wind? I probably wouldn't be up here talking about this if we could. So let's dig a little deeper. So this is taking a specific system that's a solar-heavy one where we've overbuilt and we've got the 12 hours of storage. And you see there that we've got 99% reliability over the hours of a year. But what you're looking at on the left panel here is those 36 years and each hour. And you can see it's mostly yellow because we're actually meeting demand in most of these times with that system. But as you see kind of pulled out here, one example of a week when in fact we don't meet that. And it's really tends to be the worst times in the winter in this solar heavy system. The sun is not as available in the winter. So if you don't have a lot of sun and then there's a bad wind day, that's when you get into trouble with a system like this. Couple things to note. I guess first off, look at the right panel and see when I pull out this particular week in December from a recent year, you see what happens even in this system which seems great. It gets us to 98.7% reliability. In this particular week, though, you can see the yellow of the solar coming in and out. The purple of the wind, unfortunately, is not enough to meet demand in a lot of days. And even though we have that battery in green charging and discharging, there's 5 days in a row there where you get something like 80% of your electricity demand is not being met. That's the red hatched area. So the point here is that even though we get to this very high level of reliability with this system, that's a huge amount of shortfall for 5 days in a row, and it's the kind of thing that really defines the problem of relying on renewables exclusively in an electricity system. So we need to fill those gaps. A couple things to say. First of all, 12 hours of storage, I've been throwing my hands around like that's no big deal, right? That's 12 hours. That doesn't sound crazy. Well, it turns out on average, if you consider U.S. energy demand, that means we need something like 5.4 terawatt hours of battery storage. That number probably doesn't mean that much to a lot of you. But we also might need several more terawatt hours over a few days in an outage event like this. So I'm going to say more about that 5.4 terawatt hours in a second, but just a quick note to say this was all about the U.S. We've then gone and done this in every country in the world, tried to figure out what are the dynamics at play if you're at a higher latitude or you're a smaller country or a bigger country. And it turns out there actually are a lot of differences in these cases. What share of demand is being unmet for how many hours of the year? And it does really matter if you're a big country and you can spread out your wind resources. You tend to have lower area under these curves, which is less gaps in your supply than in the case of something like Japan there in the lower right, where a lot of the hours of the year are not getting what you need. Okay, so circling back to that 12 hours of storage problem, this is actually data from a recent year showing how much battery capacity we have on the grid in the US today. And it is actually something worth noting that this is in units of power, in gigawatts. That's because typically that's what grid managers care about. They want to know how much battery capacity they have so that if there's a dip in the amount that's being generated, they can call on that storage and fill that gap immediately. Unfortunately, what we care about and what I've been talking about is the total energy. How long can they persist in delivering that much electricity? And so if we assume all of these batteries are 4 hours, that's about 200 gigawatt hours of energy. And I think that's probably a drastic overestimate. A lot of these are not 4-hour batteries. But you might be able to squint and make out that I've shrunk the plot here way at the bottom to make the point that 5.4 terawatt hours goes from this amount that maybe we're generously thinking we have today up here. And that's just to get the 12 hours of storage. So something like close to a 30x increase in how much batteries that we currently have would be necessary, not to fill these long duration gaps, just to get us to that 12-hour system. And then we'd need something like maybe twice as much to fill those gaps. So I think I'm trying to make the point that I don't think this is actually going to be how we fill these long duration gaps. And maybe another simpler way to do this is to say, how would we back these up? Maybe it's batteries, but use this example. If your extended family was going to visit you once every few years, would you go out and buy a bus and then just park it in your driveway and wait, for your family to show up 2 years from now? That seems silly, right? That's exactly what we're talking about when we're thinking about these batteries. These are rare events. Maybe they're happening once every couple years or once a year, but we're probably not going to build all those batteries and then just sit around waiting. That's a foolish thing. In fact, every extra battery we add to the grid is actually cannibalizing the demand for that battery because the events that they're filling, the gaps that they're filling, are progressively rarer and rarer. So the economic value of owning that bus or owning that battery is actually less the more we build. So what we really would like, given that these backup resources to fill those gaps are going to be used rarely, but there's a large amount of demand that they have to fill, is something that has more variable costs than fixed costs. This is that, in other words, you'll only pay for it when you're using it, not just to own it. So you'd rent an Uber, you wouldn't buy the bus, to use that analogy. And really, it's like the natural gas that we're using today to back us up, but of course without the CO2. So things like geothermal and hydro often enter in the generation side of this, perhaps. At least that's the discussion. On the storage side, you can kind of look at how these costs of different storage technologies change as we use them less and less. So on the right side of this plot is when we're cycling something daily. And as we move to the left, we're cycling it less and less over the course of the year. And maybe it's cycling only a few times, and you can see that in that case, lithium-ion batteries, even in this aspirational cost of the dashed green line, are really expensive. In contrast, something like hydrogen, if we can get it cheaply enough, starts to look pretty good. So you might ask yourself why? What's the difference between those two energy technologies? And this is something that one of my postdocs now, Jackie Dowling, has explored in some detail. And the real punchline here is what you want is an energy storage technology that's dominated by how quickly it can charge, not how much that charge is. So by that, what I'm getting at is that we might build an electrolyzer that can trickle out hydrogen very slowly for a lot of the year until that one instance when we need to discharge that storage. The reason we would just trickle it and use it slowly is because the cost of hydrogen tends to be the electrolyzer itself. And so if we can buy a small one, it's actually pretty cheap. And so Jackie put this in an energy model that was actually looking for the least cost system, and you can see exactly the behavior that I'm describing. So this is on the bottom a lithium-ion battery, and on the top something like a hydrogen storage system. And you can see that those electrolyzers might charge, like I just said, for many months very slowly, and then be discharged during those days when you actually need it, in the fall in this case. Whereas batteries on the bottom are actually cycling on a nearly daily basis. They're coming in and out. They're balancing the night, the short duration storage needs. So these things behave very differently for that reason. So to wrap up this first part of the talk, when we're thinking about the tough stuff in electricity, it's not the solar and wind. When the wind's blowing and the sun's shining, it's going to be dirt cheap. The question is the variability that I hopefully have convinced you is a geophysical phenomenon that's really unavoidable. And so I sometimes describe this to my students as a hot potato, right? There's going to be times when supply is not going to meet demand. We have options for how to close those gaps. We're not just going to not have electricity. We might build firm generation like that geothermal plant. We might ask people to turn down and demand less electricity during those times, or we could build lots of storage. And I guess I'd argue that it's not super obvious yet which of these options is going to prevail. So this is just some takeaways, but basically what I just said. Okay, so let's turn the page from electricity and talk a little bit about these structural materials. I think I already said cement and steel, so I kind of let that spill the beans already. But cement first is about 8% of global CO2 emissions, and I think maybe you know that the challenge with cement, well, there's a few. One is that it's a process that takes very high temperatures, so upwards of 1,400 degrees Celsius. And that temperature is often being provided by fossil energy, but only about 40% of the emissions from cement are related to the energy to achieve those temperatures. The other 60% is actually coming from the reaction that's involved itself. And you see it there in the calcination reaction that I have listed. Essentially, to make cement, we dump limestone in the top of this kiln, we heat it up to that high temperature, and that drives CO2 off of the calcium carbonate and leaves behind calcium oxide, which is the sort of special sauce that makes our cement stick. And so that's the process, and the chemistry itself, as you can see, is contributing more than half of the emissions from cement. So it's a hard thing. Even if we imagined decarbonizing the heat inputs, we still have to grapple with these process emissions. And it's a similar story for steel. Steel, in a blast furnace at least, we add iron ore in there. We need to reduce that, get the oxygen off of that iron. And to do that, we dump in coking coal, typically in a blast furnace. That coking coal has carbon. It's reacting, it's heating up, it's actually burning to some extent. And it's also oxidizing by pulling off the oxygen from the iron. So we get a lot of CO2 from that process. So again, we have high temperatures, we have some amount of emissions from the energy, but the lion's share of the emissions from steel are actually from the process itself. So these are difficult then because even if we come up with an energy source that's decarbonized, we have to deal with these process emissions. Let's talk for a second first about the heat. So this is actually from a paper that was looking at the challenge of reaching high temperatures for industrial applications. The plot's showing along the bottom, the x-axis, the temperature that you're actually achieving with different types of heating technologies. And they've converted it into a fuel cost, or dollars per megawatt hour of thermal energy. And you can see that heat pumps actually are fairly cheap, fairly affordable at low temperatures, say 100, 200 degrees Celsius. But those things get far more expensive if you try to get to temperatures like 1,000 or upwards of that. Instead, what you can notice is that fossil fuels there, natural gas and coal, are actually very cheap by comparison to the electrical technologies to get to those very high temperatures. And this is the challenge for decarbonizing a process like cement or steel from the heat perspective. So focusing even on that, what I thought might be the easier challenge of the energy to get that heat, we still have an economic hurdle here to get at those 1,500 degrees C temperatures. It can be done. You see electrical resistive heating can reach those temperatures, for example, but it costs quite a lot more. The lucky thing is this is showing here the cumulative distribution of CO2 emissions in blue and heat in red, and showing that we do actually have the lion's share of CO2 and heat demand at the lower end of these temperature ranges. So it's a special problem for cement and steel, but it's not to say we can't get a long way with something like heat pumps for other industries. So what to do? Well, let's pretend we actually figure out that heat problem and we come up with some technologies that are cost effective to provide that heat. We still had those process emissions. One potential solution there is something that we're already doing at considerable scales, which is called direct reduction furnaces. And so it's a different process. So it's a little lower temperature you can see here. But really, it's because it's still operating in the solid state, we're still reducing that iron ore, but we're doing it with a gas, usually something like natural gas. But increasingly, people are interested in doing this directly with hydrogen. Hydrogen rather than natural gas because there's no carbon on the molecule, and so we can actually get that reduction without the CO2 coming out of the top. And that picture in the upper right is actually a demonstration facility in Sweden where they're doing this at scale already. So it's possible. It comes at a cost premium, and it's especially large cost premium to make the plant like this hybrid facility. It actually turns out that over its lifetime, the cost per unit of steel it's producing is actually not that high. It might be $200 or $300 for a car's amount of steel. It's just a matter of de-risking the industry and proving that someone wants to buy that green steel. For cement, there's a couple options. One is just sort of marginal improvements by substituting other things besides that calcium oxide into the cement, things that don't have as many CO2 emissions like calcined clays, and you can reduce how much of that calcium oxide or clinker that you're using. That's great. It's obviously something that we should do if we can be more efficient, but it's not going to get to zero calcium oxide, so it's really not a long-term solution for net zero. There's also opportunities to actually just change up the chemistry entirely. So maybe we aren't using calcium carbonate limestone in the making of cement. We use something like calcium sulfoaluminates, or sometimes people are talking about calcium silicate rocks of other kinds. So the feedstocks there in some cases can be challenging, but really I would say that the challenge with this comes down to the conservatism of an industry like cement. If you stop to think about it, this is the stuff that's holding up the building we're in, the bridges that we drove over to get here, skyscrapers. It's the kind of thing that we could tinker with the recipe and maybe it would work, but we have a long-standing record with the Portland cement that we use today, and the industry itself is a little nervous, and I think we all probably appreciate that, about playing with that recipe too much before we figure out whether it's a good option. So we're in the phase of exploring these things, but I think it's going to be a slow path. And similarly, there's other opportunities maybe to impose some carbon capture It's possible, for example, if you capture CO2 that's coming off of that process, you can actually make a carbon negative product, because it turns out the cement, when you make that calcium oxide, over the life of cement, it's reabsorbing the carbon dioxide that you drove off when you first heated up the limestone. And so it's sucking that out of the air slowly, but that could actually mean that you're getting net negative if you capture the CO2 to start with, and that's something people are exploring. So all of this is to say, for these structural materials, we have different options that can make different inroads. We had a paper that kind of boiled this down and thought about it in terms of a skyscraper. So this was looking at a 30-story building, which amounts to about 6,000 tons of CO2 from iron and steel alone. And we looked at how much could we get that number down by just being more efficient with our use of the materials and substituting alternative materials that had cementitious properties, for example. And maybe a third of that could actually go away just by doing that. Maybe we would, to get further though, need to do these alternative processes, which we may be nervous about if they're not producing a similar product to what we've been using. The heating is less of a factor, but something that I think we could get to. For example, it is possible to get those high temperatures fairly affordably, not necessarily with the electricity, but with biomass or even municipal solid waste some people want to use to heat up cement kilns. But really, I think to get all the way to net zero, we'll need some amount of carbon capture and storage. And there are some technologies that are trying to optimize for this. This LILAC is one that does the heating of the cement kiln electrically so that you don't have combustion exhaust products mixed into the CO2 that's being produced by the chemical process. And then because you have a purer stream of CO2, it's cheaper to actually do the CCS. And I just mentioned, I already did mention briefly that we have this reverse process of calcination called carbonation that sucks up some of the CO2 over the life of the cement. That's something that we've looked at in my group about how much of that's going on around the world. And it turns out there's about 1 billion tons of CO2 a year that's going into cements that we've built historically. So it's a non-trivial amount. We also, and I think Adam mentioned this in his introduction, had a paper this year looking at whether you could take something like biochar, for example, and use it as the aggregate in your cement to help lock away carbon in a way that could store it semi-permanently. And the scale of cement we use, which is on the order of 5 billion tons a year, means that you could actually do a lot of that and lock a lot of carbon in the materials itself. So that's another opportunity here that we're exploring. We're also looking a little bit at where all of this is happening. We've had a couple papers lately kind of looking at where different cement kilns, or in this case, steel-making facilities, are located, and trying to identify those that have disproportionately high emissions relative to their production. So trying to make a to-do list for policymakers. You can see from that map here, I'll mention, around half of steel and cement are made in China. So a lot of the action is going to happen there, if anywhere. All right, so with the structural materials, I've made the case that the difficulty really has to do with these high temperatures, also the process chemistries. And there are a lot of different things that we can do. Some of the big challenges are when we want to make huge gains, we either have to change the recipe and we have to deal with the consequences of that or the risks of that, or we need to do a lot of carbon capture and storage, which has not always been politically palatable everywhere. But that's the story with these structural materials. So I'll finish up by some conversation about the transportation piece. And so I mentioned, that we were mostly not looking at the light-duty vehicles because we think EVs are going to win that. But there are other types of transportation, and really the challenge boils down to energy density. So jet fuel, for example, has about 45 megajoules per kilogram, but lithium-ion batteries, hopefully you guys are familiar, have much, much less energy density, something like 1 megajoule per kilogram. Similarly, it's not just mass, but in terms of volume, jet fuel being a liquid has about 33 megajoules per a liter, as opposed to something like hydrogen, which even under modest compression still has far less, 0.01 megajoules per liter. So this is helping to define the problem. If we wanted to fly an airplane, obviously we're talking about jet fuel here, We'd really have a problem if we tried to do that with batteries or with hydrogen gas, especially the really big ones, and I'll say more about that in a second. Fundamentally, the problem is something that you can actually sort of intuit, and that is that when we're driving a car or a jet like this and it's an internal combustion engine, we have a reaction happening where we have a fuel, we're mixing it with air, and then we're putting the exhaust out the back of the engine or out the tailpipe. So when we look at that A plus B and make C, we're only carrying one of the reactants with us on that jet. We mix with air that we're bringing in that's free, when you're in the sky, and we're putting the exhaust out the back. In contrast, if you're thinking about a battery, the battery is self-contained and it has to hold all of its reactants and products. So even if it's a really great chemistry, it's still just inherently disadvantaged with respect to energy density because it has to carry everything in it. So when we've been thinking about this, and I actually would have said when we first wrote this paper back in 2018, we thought a lot of a longer distance transportation was going to be challenging to electrify. I might have even doubted that something like these prime trucks that we now see all over would be so readily electrified. So one piece of bright news is that some of this might be more possible than we think. Where we were really worried was for the longer distance things. And so you can do kind of back of envelope calculations, for example, and where long range is important, like it is for some of these long distance trucks, Class 8 trucks, electrification comes with a big penalty of how much you're carrying in the truck. So for an average lithium-ion battery density today, if you wanted to maintain the 700-mile range of this kind of semi-truck, you would need to take up about a third of the payload with batteries. And that's obviously going to take a bite out of your economics. You're going to have more trucks to move the same goods around. People have actually been modeling this, though, and doing some pretty careful work looking not just at that penalty, but also things like charging times, impacts on the grid, air pollution benefits, and all sorts of things. And they're increasingly convincing me that we might actually be able to come up with technologies that could be fast charged, or maybe there's modular batteries, or we sacrifice a little bit of that range and we're able to solve that problem. So I'm increasingly bullish on electrifying even the heavy-duty trucks. I'm a little less bullish on things like this ship, though, the container ships that have to go out to sea for weeks at a time. I think that the penalty there is going to be sizable, and so we're doing some work on that now. But I think I'll wrap up today talking a little more in detail about aviation, which is really the hardest case to make for getting to a net zero system. So to really bring this point home about energy density, these two jets are some of the biggest jumbo jets that we have, the Boeing 777 on the top and the Airbus 380 on the bottom. And what I'm showing on this bar chart is how far these two different model of airplanes can fly. And so with fossil jet fuel, you see they're both well above 12,000 kilometers in their range. And I've added the distance from LA to Beijing there just for some context. Now, we did some calculations to figure out if you constrain the mass of these aircraft and you instead try to get the energy you need from hydrogen or batteries, this is the distance that you can take those two different aircraft. And you'll see there's a little bit of a lighter color shading on the end of each bar. This is where we've estimated that maybe there's actually a considerable increase in the efficiency of those engines. So giving credit for that potential. But you see they're both far, far short, especially the batteries, from anything you'd want to do to make it across an ocean. So there's a lot of hype around companies that are going to do electric aviation, and if you've paid attention, you'll notice they're all like these tiny sort of commuter jets that are going to go from LA to San Francisco, or maybe not even that far. It's LA to San Diego or something like this. And I don't think those are technologically out of the ballpark. Obviously, people are pursuing them. And you've probably heard Airbus and others hyping the opportunities to do hydrogen in their jets, but I think this plot to me convinces me that we're not going to get on a large jumbo jet and fly across an ocean anytime soon without liquid fuels on board. And so that really sets the sort of stage for this last piece of the talk. So just to step through these three plots, this first one is showing you aviation demand The gray part on the left is the historical demand. You can see it's broken down by passengers and freight. You can even see the dip of the pandemic there. And then those three colored lines going up are just future projections where we've tried to bound what we think is a realistic future projection of demand. The business as usual has taken economic projections and saying if historical relationships of per capita income and those economic projections apply with respect to the aviation demand, that's what business as usual would be. The blue is actually from industry projections that people have made, different airlines and the ICAO, the Civil Aviation Organization. And then the low one is something that we did where we said maybe all of the shorter distance trips could be electrified, or maybe we're riding on high-speed rail. We're not taking a flight when we want to get to Los Angeles or San Diego from San Francisco anymore. And we've maybe also convinced people to fly less. So we really kind of did our best to get demand down in that ambitious scenario. And I thought it was interesting that we still didn't manage to overall reduce the total demand, because a lot of places around the world that haven't historically flown very much are getting richer, and there will be demand there. The middle one is looking at how energy efficient are airplanes. So over time, we actually have gotten better at using less energy to move people and freight around. And so you could imagine those trends continuing. Of course, neither of these is ever going to get to zero, right? We want to get to net zero. That's where I started the talk. So to get to that, we really do have to imagine switching what kinds of fuels we're using for our planes. Here, the black line historically is essentially flat because we've always used jet fuel, at least within this time period. In the future, we could keep using fossil jet fuel. That's the carbon intensive path there that stays flat. Or we could increasingly supplant that fossil jet fuel with other types of fuels. And these are what has really come under the name sustainable aviation fuels lately, which I'll say a little more about. So all of this is to say there's this range in the future. The only way we'd get to net zero is by using a lot of these sustainable aviation fuels. And this plot on the right is showing how much we might need depending on some of those other assumptions. You can see in the horizontal dashed line the amount of biofuels we used globally in 2019, and hopefully make out that either the industry or business as usual projections blow past that amount. In other words, even if we successfully electrify all of our light duty vehicles and we have all that ethanol available that we've been using for vehicles on the road, and we put all of that into planes, we'd still be far short of the energy we need for most of the projections. So what are the options for SAF, or sustainable aviation fuels? These are sort of the two that people talk about. The left one is a biofuel called HEFA, and the right is an e-fuel where we actually capture carbon from the atmosphere and we use electricity to make hydrogen, and we put those things together and synthesize our own jet fuel such that when we burn that jet fuel, we're adding CO2 back to the atmosphere that we already took out. So that's how we get to a net zero situation. Same thing is sort of going on, we hope, or at least in theory, with a biofuel. The plant takes the carbon out of the air. We make a fuel out of it. When we burn it, it goes back. What these plots are actually showing on either axis is some of the cost drivers related to these, and the contours use the same color map to show the cost per liter of these different SAFs. So you can just tell at the outset that the biofuels look cheaper, right? The colors are cooler. Something to note is these dashed lines here are showing the current cost of fossil jet fuel. So it's kind of what we would like to get to if we wanted to be cost competitive. And you can see that up in the upper right of either of these is kind of the current cost, at least maybe it's a little bit on the high side, but the current cost of these two. And you can see that there I've drawn the arrows of how much we might need to reduce on both of these in order to be cost competitive. So on the left, we're talking about how much does the bio feedstock cost, how efficient are we in making a fuel out of it. Those are important dimensions. On the right side, it's how much can we capture carbon from the atmosphere for, and how much can we get green hydrogen for. And really, I'd say that the biofuels are the more cost competitive strategy, but they're supply constrained. And if we really wanted to scale them up to the degree that I showed you on the previous slide, I think we'd start worrying about environmental problems of using more land, having less area available for agriculture, and so forth. On the right, we just really need to get both carbon capture and green hydrogen much, much cheaper to really make a case for that. It's also important to know, you've probably heard people talking about SAF. I know I see these ads when I fly on United with Oscar the Grouch, my childhood favorite. And they're talking about how they're making SAF. Something important to know is that it's really a tiny, tiny amount of the current fuel that's SAF. Something like 0.1% of United's fuel in particular is SAF. And it's limited in its availability. It's only in a few airports around our country yet. It's also something that the definition of SAF, according to this ICAO, is that it's only 10% less carbon intensive than jet fuel. So far from the net zero fuel that we might like. So it's important that we not mistake that this is success. There's another practical challenge going on right now, which is the organizations that are setting standards to allow companies to buy into this and book and claim, they call it, a credit for SAF, are not allowing that to happen unless the company can prove that it was burned on the flight that they actually took. And so I think that's chilling some investment for SAF right now. All of this is to say, you can start to think about aviation as being hard enough and expensive enough that it might actually make sense to keep burning jet fuel and use carbon dioxide removal technologies to actually compensate for the CO2 that's coming out of the jet. This plot's showing you what that looks like. So the cost of a sustainable aviation fuel is on the x-axis, and the cost of carbon dioxide removal is on the y-axis. And you can see that this white line is the dividing point at which either CDR is going to be the cheaper bet or SAF. And so if we're still paying something like $2 a liter for SAF, and we could actually do better with CDR if we could get CDR costs under, say, $300 a ton, which doesn't seem completely implausible. So I'll leave it at that. So I think I've been long-winded enough. I'm sort of running out of time. But briefly to mention, there's not just the emissions from aviation. We also worry about warming related to contrails. Doing some work with Breakthrough Energy right now to try and understand which flights actually have more contrails. It turns out that the warming contrails are really concentrated in less than 10% of all the flights around the world. And if we could identify those, then you and I might actually opt into flights that are less likely to have those contrails, or the airline companies might be able to do something to avoid those. So one thing here, just to throw it out, is that they tend to be worse at night. The reason being is that in the daytime, some of the incoming sunlight could be bounced back by a contrail, but at night, that's never an option. They're only ever going to trap heat at the surface and warm. So avoid the red eyes if you can. All right, so I think in the interest of time, I'll just move on and wrap up my talk, which is to say that, what these difficult things mean in the current context, where maybe you're all sitting here thinking net zero is great and all that. I was on board 6 months ago, a year ago, but we're now in a different world. We're seeing a lot of pushback on some of what used to be ambitious climate goals. In particular, we know that the Inflation Reduction Act has gone away, and we have the One Big Beautiful Bill that's kind of undermining some of the subsidies and momentum that we had for renewables. It's also the case that some companies and things, I think, are sort of dialing back. But my point would be here that people have modeled this, and despite all of that, we do get less clean energy in EVs, but we still are anticipating a lot there. And I think it's not something that I'm actually terribly worried about yet. This is actually a plot of what's going on in electricity generation in the US right now. And what you can see here is that solar is really taking up all of the new demand for electricity that we have in the country. If you kind of make out the percentages in this plot, like natural gas is staying constant, nuclear is staying constant, hydro is staying constant. The only one that's growing is solar. And this is updated and projecting out to 2026. So even though we have some headwinds right now on the climate front, I think those things that I'm calling easy are still going to be there for us, and we're still going to see a lot of them in the future. Which is to say that it may be sooner or it may be later, but these tough things that I'm talking about, the difficult things, are really going to define the finish line for us. And it also means that they're where the frontier of innovations are going to happen. There's lots of exciting companies, startup companies working on just these kinds of difficult things. How much they can reduce the green premium, in other words, the extra cost to be clean, is really going to define our success to get to net zero. And I apologize for going over time, John. Yeah. Thanks, everyone. Yeah.
Thanks, Steve. We could probably do a couple of questions in the room here still, if there are any, particularly students. Let's do these two, and then Holmes. Three. So I lied.
This is like a very specific question because I work in hydrogen.
Sure.
I'm wondering if the numbers are about compressed hydrogen in terms of energy density, or if it's, and how specifically evolutions and how we are able to compress, contain, and hold our fuels affects the aviation market in particular, because I think that there's a lot of questions specifically about liquid fuel versus compressed gas fuel and how that affects energy density performance.
Yeah, so I think the number of energy density that I threw out was 30 bar or something like that. But the deal with hydrogen is this: you can compress it more, of course, but when you do that, you need a stronger vessel. And if you're going to do cryogenic, that sounds even better, but then you have to have all that refrigeration technology. So the energy density penalty that you get in order to compress it ends up eating into the gains of compressing the gas itself. So you don't actually benefit that much in terms of energy density by compressing. So, yeah.
Okay, then right next door. Good.
Yeah, I was just wondering, thanks for a great talk.
Thanks.
If you could comment on two technologies. So one is mass timber construction, and then the other is for freight electrified rail, like thinking about that as a pathway. Just
Yeah.
like what's the potential for those?
I mean, I'm a big fan of mass timber construction. I think it's really cool. I'm a fan of wood. It's a beautiful material. I think it's hard to imagine that we'll actually get to the point where we're going to make up, though, for all of the cement and steel that we're currently using for buildings with wood. I think it would be a wonderful world if we were able to do that, maybe. At least the cities would look a lot nicer, but our forests would probably suffer quite a bit, right? We use on the order of 4 billion tons of steel, I think, and 5 billion tons of cement. So just think about that in the scale of replacing it with wood. Even if we could overcome engineering and design challenges, I think it'd be a hard thing. Remind me, what was the second technology?
Yeah, freight to rail rather
yeah.
than trucks. Yeah.
I think, again, I think freight is something that if we could get electric trains running a lot of places, we could do a lot of good there. There are challenges where you might need to hybridize and have some sort of a fuel cell on board or something to give you an extra boost to get over certain passes and things. It's also just hard to build rail. Like we've not built a lot of rail. We know this very well in California, right? How many miles of high-speed rail have we built in the last 20 years? So I think it's a great option, but it would be a challenge maybe to get it all built. So.
Okay, one last question.
Yeah.
Great talk, Stephen. Holmes Hummel with Stanford Energy. On slide 14, you tempted us with a heading about demand flexibility with no comment. May I give you in this Q&A an opportunity to speak to a part of your research portfolio that maybe could still yet be developed to be applicable in that area?
Holmes is after me to submit an efficiency proposal, I think. Yeah, I think it's a really interesting opportunity. The challenge with demand management is those gaps that I was showing are substantial enough that it's not just Adam turning off his fridge for 5 minutes. It's really large loads that would need to be shed. And in order to do that, usually you have to get to an industry where it's a very capital intensive industry that's shutting down. And so you still have this concern of you're idling something that's capital intensive and you're just, it's the hot potato. Who can bear that potato the most? The one caveat I would say is, grid-connected electric vehicles might be a sufficiently large load that could be a really exciting opportunity for demand management if we could convince people to connect their cars and let us manipulate the batteries.
That'll have to be good enough for today, Holmes. So with that said, let's thank Steve one last time.